Someone mistakenly put a lovely couch out at the curb on garbage day, and you decide to take it back to your apartment. You push on the 80-kilogram couch with a force of 320 newtons directed at 15 degrees below horizontal. The frictional coefficient is 0.4 for static and 0.35 for kinetic. They always give you the coefficient of static friction first, and in your book, the coefficient of static friction is always greater than the coefficient of kinetic friction. That is almost always the case, but does not have to be the case. Okay, so we have the couch here. We're going to draw the free body diagram. We have the force of gravity acting downwards. The force of gravity is equal to the mass times g. In this case, the mass of the couch is 80 kilograms. We multiply that by 9.8, and we get 784 newtons. And all the other forces that we have come from something which is in contact with the couch. The ground is in contact with the couch, and it exerts a normal force called the normal force because it is perpendicular to the surface of contact, and normal is another word for perpendicular. We also have a force from the ground which is parallel to the surface of contact, and that is a frictional force. I do not know whether or not the couch moves. If the couch moves, this is a force of kinetic friction. If the couch does not move, it would be static friction, so I'll just call it F sub F until I figure out whether or not this is static friction or kinetic friction. You are pushing on the couch with a force of 320 newtons directed at 15 degrees below the horizontal. So here's the horizontal, and the force is at an angle of 15 degrees below the horizontal. This is the force of the push, and it has a magnitude of 320 newtons. I'm going to draw a new free body diagram, and I'm going to take this force and break it down into components. So we have the 320 Newton force. It has a horizontal component and a vertical component. This angle is 15 degrees. And the horizontal component is 320 times cosine of 15 degrees. The vertical component is 320 times sine of 15 degrees. 320 times cosine of 15 degrees gives me 309. And those units are newtons. And 320 times sine of 15 degrees gives me 18.8 newtons. So on my new free body diagram, all the forces are going to be broken down into components, so they'll either be horizontal or vertical. I have the force of gravity going downward. This is 784, because I already showed on my first free body diagram that this is the force of gravity. Now I'm just going to put in the magnitude of the force. This is the force of friction. I have a component for the force of the push acting in the horizontal direction. This is 309. And another component which is acting downward, and that is 18.8. Okay, now I can sum up the forces in the y direction and in the x direction. When I sum up the forces in the y direction, this is equal to the mass times the acceleration in the y direction. I do not know whether or not the couch is sliding on the ground, but if it is sliding on the ground, it would only be accelerating in the x direction, if it is accelerating at all, unless it's going into the surface or coming up off the surface. It does not have any acceleration in the vertical direction. So the acceleration in the y direction is equal to 0, therefore the sum of the forces in the y direction is equal to 0. Therefore, the upward force must be equal to the downward forces, or you could say if up is positive, the normal force minus 82.8 minus 784 is equal to 0. Or you could just immediately say if the upward force is equal to the downward forces, the normal force is equal to 82.8 plus 784, which you get from this equation when you bring the 82.8 and the 784 over to the other side. And that gives me, for the normal force, 867 when I round. This is in newtons. Remember, this n is the normal force, and this N is newtons. And if you don't like that, instead of calling this normal force N, you could call it Fn and say the normal force is 867 newtons. So if you find that less confusing, you could do that instead. Okay, so this was in the y direction. Now I got to go back and look in the x direction. I know that the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction, but I do not know whether or not the couch is moving, and so I am going to have to figure out if the couch is moving. Because the coefficient of static friction is greater than the coefficient of kinetic friction, if you assume the couch is moving to begin with, you will be able to find the acceleration in the x direction, but you have to push the couch harder to get it moving, then you have to push it to keep it moving at a constant speed. So first we want to check to see if you're pushing with a large enough force to overcome the force of static friction and get the couch moving. So we are going to assume the couch is not moving. If we assume the couch is not moving, then we can figure out what this force of friction is, and that would be static friction if the couch is not moving. And if the maximum value for the force of static friction is greater than or equal to the force of static friction that we find assuming that the couch is not moving, then the couch is not moving and we can be done. If the force that we would have to have in order to keep the couch from moving is greater than the maximum value for the force of static friction, then our assumption is wrong. The force of static friction can't be that large and the couch is actually moving. And then we'll have to look at the problem again and use Newton's second law with assuming the couch is moving and using kinetic friction. So first, assuming the couch is not moving, the acceleration in the x direction is equal to 0. Looking in the x direction, I only have two forces. So I would have for Newton's second law, if that is the positive direction, 309 minus the force of, now it would be static friction if the couch is not moving, is equal to 0, since the acceleration is equal to 0, or I could just say 309 is equal to the force of static friction. Now I have to check to see if this is possible. So I need to check to see if the maximum value for the force of static friction is greater than or equal to the force of static friction that I just found here. And remember that the maximum value for the force of static friction is equal to the coefficient of static friction times the normal force. So I need to figure out what the maximum value for the force of static friction is. The coefficient for static friction is 0.4. So this is 0.4 times my normal force, which is 867. And that gives me 346.8. So 346.8 is greater than 309, so the couch does not move. Which means our assumption was good and we can stop. If the force for the maximum value for the force of static friction was less than 309, then I'd have to go back to Newton's second law. This force would be kinetic friction instead of static friction, and my acceleration would not be 0, but I could use the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. And I could put that into Newton's second law, and then I can solve for the acceleration. So if the couch did move, then I would need to use this equation to find the coefficient of kinetic friction and use Newton's second law in the x direction to find the acceleration in the x direction. Okay, so this problem was easier because the couch does not move. We will see examples next class where the couch does move, and we'll have to go back and use Newton's second law with the force of kinetic friction.